Hey guys. Whoa. Greetings, my fellow geothermal students. Here we go again, man. We're into topic 8 now. I've started to get towards that midterm exam, so look ahead in your course here. I'll open that up for you. You can look ahead and see when we're going to have that midterm exam. It might be out there in topic 11, or week 11. Hopefully you're getting at some information on your median temperature lab. You're getting that going and got it cited, and you're making some recordings and getting ready to log some data. The term paper, be thinking about that. And remember, extra credit. If you guys can find a topic that I haven't touched on, I'm going to try to get them all, okay? At least brush on them. And this is Introduction to Geothermal Energy. I'm Jonathan Bowe. I'll be your instructor. And let's delve into it today. Here we go. Topic 8. Hoping you're finding everything conveniently in your central column of your course. Sometimes these topics on the outside here go off on a tangent of their own. So if you're having any difficulties, stick with the central column here. And the current week will be highlighted. Here we are, week 8, topic 8, learning unit 8. So let's remember to get that median temperature lab fired up. And you see here that now is the time to graph your data for your temperature data. Collected twice a day for 14 days, 14 entries for temperature 6 feet below ground, 14 entries for temperatures collected on the surface. So a grand total of 28 entries. And you can use local weather for your surface, high and low temperatures. Total entries should equal 28. And there'll be a submission link in the future here. So that'll be graded at that point. But do be collecting that data so that you can take advantage of the median temperature lab. So we're going to look into some fracking techniques today. Remember last week we looked at some earth cooling, earth slinky, the residential applications. Well, you know, and the enhanced geothermal systems, EGS, that's going to be a big one for us. But just in relation to enhanced geothermal systems, fracking is a technique that's very important. Let's take a look at some fracking here.
Hydraulic fracturing, more commonly known as fracking, is a process which allows natural gas to be extracted. Fracking has proven itself to be helpful in alleviating some dependence on the importation of foreign fuels, and is a stepping stone toward new technologies and energy independence for the United States.
You see, this is for oil they're talking about here, but remember, one of the things that we consider is repurposing these fracted out oil and gas reservoirs. So the techniques for geothermal fracking are very similar. Sometimes we go deeper when fracking for geothermal to get more heat further down. But the oil degrades at certain temperatures, so that, but there's still, these fracted out reservoirs are still deep enough and produce enough heat that we can use binary plant generation, where you use organic compounds that boil at lower temperatures to run your turbines. Likewise, you don't have to run that saline solution or that dirty steam through your turbines. You have a cleaner system. You re-inject the fluids then, and this is the same technique we use for oil and gas.
Until recently, pockets of natural gas have been lying approximately 1.5 miles beneath the surface of U.S. soil. Fracking allows us to recover this resource and bring relief to the ever-growing energy crisis facing the U.S. The The fracking process has been used or is currently being used in a number of states. The process begins with drilling a borehole into the earth to a depth of approximately 1.5 miles, or about 7,700 feet below the surface. Safety is a top priority, and precautionary measures are in place surrounding the borehole, such as protective steel casing, as well as additional cement casing at groundwater levels. To help visualize the extreme depths at which extraction occurs, imagine you are standing on the observation deck of the Sears Tower, now known as the Willis Tower in Chicago, Illinois, and you are looking down to the streets below. Now imagine 5 of the Willis Towers stacked on top of each other and looking downward from that distance. 5 Willis Towers stacked vertically are the equivalent of 7,700 feet, the approximate depth at which extraction occurs. One of the main concerns voiced by those opposing fracking is the potential to contaminate the underground water supply. Preservation of groundwater quality is the first priority in the fracking process, and this is addressed by placing additional steel and cement casings around the borehole to prevent leaks in the aquifer. As the borehole is drilled into the ground, it passes through many different layers of earth and several thousand feet of solid rock layers. These rock layers, such as granite for example, are extremely dense and therefore not affected during the fracking process. The density of those layers acts as a natural barrier between the shale layer where the extraction occurs and the groundwater level, and thereby will prevent any natural gas or chemicals from seeping into the groundwater supply. Once the borehole has drilled down to the shale layer, perforating tools are then guided down the borehole carrying conductors. Once these tools are in place, the conductors emit a shock wave into the shale layer. This shock wave causes slight underground fractures in the shale layer. These fractures are also known as fissures. Once the fissures are created, the perforating tools are removed and brought to the surface. Water and sand are then blended with additives in preparation for insertion into the borehole. This mixture is made up of over 99% water and sand, and less than 1% other additives. The water and sand mixture, or proppant, is injected into the borehole and travels down the depth of the borehole into the shale layer. The pressure caused by the water mixture allows the fissures to expand. Most of the water mixture is extracted and stored in a storage reservoir. However, a small amount of proppant is left behind, which consists mainly of sand. These small particles help the fissures to remain open. The open fissures make it easier for the natural gas to be extracted and flow towards the surface. The natural gas is collected in reservoirs, then pumped into container trucks and hauled away from the fracking drill site. The water and sand mixture is combined with a very small portion of chemical additives. These other additives make up less than 1% of the mixture. These additives can be found in products we use every day, such as laundry detergents and soaps, household plastics, deodorant, disinfectants, cosmetics, acrylic fibers, and food additives. Fracking provides a valuable energy.
So, one point there, not all fracking solutions are super poisonous. You know, I mean, any of these things we're looking at here, no, it's not good to eat laundry soap. You wouldn't want it to be in your water, you know.
We use every day, such.
And one of the proprietary, the top secret fracking solutions is Calgon bath oil beads, because they have a tendency to expand, and that's the whole idea. Is that you start using nanotechniques, chemical techniques to expand and jack open the fissures.
Such as laundry detergents and soaps, household plastics, deodorant, disinfectants, cosmetics, acrylic fibers, and food additives. Fracking provides a valuable energy source for the United States. Natural gas is a clean fossil fuel. Using natural gas as an energy source in lieu of other energy sources, such as coal for example, will reduce carbon dioxide emissions by 17% and thus lead the United States towards a carbon-light environment. Moreover, the abundance of natural gas on U.S. soil will not only support America's energy needs for a longer period of time than other fossil fuels, it will also create jobs, stimulate the economy, and enable the United States to produce its own energy supply that in turn reduces our need to rely on foreign fuel imports. Extracting natural gas by fracking provides enormous benefits with minimal risks. It lowers energy costs and benefits the environment. The potential risks involved in fracking are minimal and are easily managed. As we have seen here, groundwater is protected by thick steel tubing and cement casing, and fracking occurs miles away from drinking water. New technologies and processes continue to ensure that safety is a top priority. As of today, current U.S. oil reserves are limited and can only sustain the energy needs of Americans for the next 9 years, which leads to a heavy reliance of foreign fuel imports. However, fracking will produce enough natural gas to sustain the energy needs of Americans for the next 100 years, bridging the gap and providing a sustainable energy resource while research continues and new technologies for additional alternative energy resources can be developed.
Hey, one of those alternatives, could it be geothermal? Yes, especially since we can repurpose these once they've exhausted these fracted out reservoirs and extracted all the natural gas or oil. A lot of times they put a saline solution back in to minimize the potential for collapse, especially if there's the geology dictates such that, you know, they can't leave an empty hole underground, because then they might more potential for earthquakes and maybe even potential for pollution of the aquifer, which would be a terrible thing. But we'll look at that, repurposing those fracted out reservoirs.
Leveraging domestic energy resources is smart policy for our country and provides the United States with the ability to be more self-sustaining. Since natural gas is an abundant resource right here on American soil, fracking provides an opportunity to lessen our dependence on foreign energy and increase energy innovation and revenue within the U.S.
Yahoo! All for it. Let's take a look at a little more graphic demonstration of fracking techniques, animation of hydraulic fracturing.
Geologists have known for years that substantial deposits of oil and natural gas are trapped in deep shale formations. These shale reservoirs were created tens of millions of years ago. Around the world today, with modern horizontal drilling techniques and hydraulic fracturing, the trapped oil and natural gas in these shale reservoirs is being safely and efficiently produced, gathered, and distributed to customers. Let's look at the drilling and completion process of a typical oil and natural gas well. Shale reservoirs are usually 1 mile or more below the surface, well below any underground source of drinking water, which is typically no more than 300 to 1,000 feet below the surface. Additionally, steel pipes, called casing, cemented in place, provide a multi-layered barrier to protect freshwater aquifers. During the past 60 years, the oil and gas industry has conducted fracture stimulations in over 1 million wells worldwide. The initial steps are the same as for any conventional well. A hole is drilled straight down using freshwater-based fluids, which cools the drill bit, carries the rock cuttings back to the surface, and stabilizes the wall of the well bore. Once the hole extends below the deepest freshwater aquifer, the drill pipe is removed and replaced with steel pipe, called surface casing. Next, cement is pumped down the casing. When it reaches the bottom, it is pumped down and then back up between the casing and the borehole wall, creating an impermeable additional protective barrier between the well bore and any freshwater sources. In some cases, depending on the geology of the area and the depth of the well, additional casing sections may be run and, like surface casing, are then cemented in place to ensure no movement of fluids or gas between those layers and the groundwater sources. What makes drilling for hydrocarbons in a shale formation unique is the necessity to drill horizontally. Vertical drilling continues to a depth called the kickoff point. This is where the wellbore begins curving to become horizontal. One of the advantages of horizontal drilling is that it's possible to drill several wells from only one drilling pad, minimizing the impact to the surface environment. When the targeted distance is reached, the drill pipe is removed and additional steel casing is inserted through the full length of the wellbore. Once again, the casing is cemented in place. For some horizontal developments, new technology in the form of sliding sleeves and mechanical isolation devices replace cement in the creation of isolations along the wellbore. Once the drilling is finished and the final casing has been installed, the drilling rig is removed and preparations are made for the next steps, well completion. The first step in completing a well is the creation of a connection between the final casing and the reservoir rock. This consists of lowering a specialized tool called a perforating gun, which is equipped with shaped explosive charges, down to the rock layer containing oil or natural gas. This perforating gun is then fired, which creates holes through the casing, cement, and into the target rock. These perforating holes connect the reservoir and the wellbore. Since these perforations are only a few inches long and are performed more than a mile underground, the entire process is imperceptible on the surface. The perforation gun is then removed in preparation for the next step, hydraulic fracturing. The process consists of pumping a mixture of mostly water and sand, plus a few chemicals, under controlled conditions into deep underground reservoir formations. The chemicals are generally for lubrication, to keep bacteria from forming, and help carry the sand. These chemicals typically range in concentrations from 0.1 to 0.5% by volume and help to improve the performance of the stimulation. This stimulation fluid is sent to trucks that pump the fluid into the wellbore and out through the perforations that were noted earlier. This process creates fractures in the oil and gas reservoir rock. The sand in the frac fluid remains in these fractures in the rock and keeps them open when the pump pressure is relieved. This allows the previously trapped oil or natural gas to flow to the wellbore more easily. This initial stimulation segment is then isolated with a specially designed plug, and the perforating guns are used to perforate the next stage. This stage is then hydraulically fractured in the same manner. This process is repeated along the entire horizontal section of the well, which can extend several miles. Once the stimulation is complete, the isolation plugs are drilled out and production begins. Initially water and then natural gas or oil flows into the horizontal casing and up the wellbore. In the course of initial production of the well, approximately 15 to 50% of the fracturing fluid is recovered. This fluid is either recycled to be used on other fracturing operations or safely disposed of according to government regulations. The whole process of developing a well typically takes from 3 to 5 months. A few weeks.
See, this is where the fluid that's recovered can be pumped into other well systems that have been depleted. That's why a lot of times they'll, if the fluids are are freshwater to start with, but then once they've been down underground, they pick up a lot of minerals and salts, and are not so pure anymore, so that they become a hazardous waste. And they pump them into the other exhausted well structures or reservoir structures, and just leave what we can use for our coolant or our circulating fluid for geothermal.
To prepare the site, 4 to 6 weeks to drill the well, and then 1 to 3 months of completion activities, which includes 1 to 7 days of stimulation. But this 3 to 5 month investment can result in a well that will produce oil or natural gas for 20 to 40 years or more. When all of the oil or natural gas that can be recovered economically from a reservoir has been produced, work begins to return the land to the way it was before the drilling operations commenced. Wells will be filled with cement and pipes cut off 3 to 6 feet below ground level. All surface equipment will be removed, and all pads will be filled in with dirt or replanted. The land can then be used again by the landowner for other activities, and there will be virtually no visual signs that a well was once there. Today, hydraulic fracturing has become an increasingly important technique for producing oil and natural gas in places where the hydrocarbons were previously inaccessible. Technology will continue to be developed to improve the safe and economic development of oil and gas resources.
And we'll use their fracted out, disposed, capped off wells and just say, hey, don't cap it, let us use it. For our geothermal, we're going to look at some of those repurposing techniques.